Welcome everyone. This is our second recorded tutoring session between me and Man Sharma. In this session, we're going to be talking about electric potential and maybe Laplace's equation. Now, to remind you, this series is a series on electromagnetism. Over the course of the years, I've thought very deeply about electromagnetism as I tutor it to lots of students, and during these tutoring sessions, I have constantly been trying to connect these mathematical abstractions that you're usually taught in physics classes. I've been working hard to connect these abstractions back to the experimental evidence. But that's not the only thing I'm doing. I've realized lately that I'm doing something else that really isn't emphasized by anyone, not even objectivists interested in induction. And what that is specifically is the reasoning steps that take us from the experiments to the mathematical abstractions. And you're going to see concretely what I'm talking about today, because what I'm talking about today when I say this, because it takes a lot of thinking and a lot of very special reasoning to go from the experiments to the abstractions. Now, the common view on this portion of science is that basically the mathematical abstractions were invented to match the observations, and then they found out that it worked. And what we're going to see today and in many of these other videos is that that's not how it happened, or at the very least, that's not how it has to happen. We can proceed with much more confidence than that, identifying mathematical abstraction, or first thinking about the experimental evidence, then forming hypotheses, then making inferences from the existing evidence to identify these mathematical abstractions. And finally, what we're going to be doing is going further than just the mathematical abstractions, going further than just fields. We're going to be making hypotheses about how these fields might be properties of the ether. Now, these are just hypotheses, but what I find is that this achieves two goals by bringing up the hypotheses. Number one, it's a strong pedagogical tool. Fields are very abstract, and it's really hard to remember, to hold in mind, like, what do these mean? Like, what are these? I remember when I was Mon's age, I struggled with that question constantly, and the answers I gave were all wrong. They were just all incorrect. And that's because I didn't have a rooting in broad physical categories at the time. I hadn't come up with them. Or read any philosophers that had sort of equivalent works to broad physical categories. If I had read Aristotle carefully, I would have understood that fields can't just exist on their own. They have to be a property of some entity. Aristotle would have been able to, say that, although, and if I read Aristotle carefully enough, I probably would have figured that out. But I figured it out eventually, and now I'm explaining it to y'all. So that's one advantage of going through the hypotheses for what this might have to do with the ether. The second advantage of this is that I'm giving out actual hypotheses about what the ether might actually be doing. And even if they're wrong, and they're very likely wrong, they still give us a sense of what it would look like to identify the entities, properties, and actions that lie behind these mathematical abstractions, which lie behind vector fields like the electric field and scalar fields like the electric potential. So, and what that does is it helps you. It's hard to even, with the way most of us have been educated, it's hard for us to even understand what it would look like to look at this as a real physical phenomenon, not just as a set of mathematical abstractions. So with that, let's get into our next subject in this series, and that's going to be electric potential. So there's my doodles. Let's see. Let me think about this. So here's my introduction to this subject. We've already discussed electric fields. Okay, and we've discussed, and with Gauss's law, we've discussed the possibility that the electric field is some kind of emanation that radiates outward from the charge. Okay, now, Mon, I'm forgetting, have we discussed how the charge might have, either has or has not, unlimited ammo? Have we talked about that? The issue of unlimited ammo. We did? Okay, good. So, oh, that was the end. So y'all can go to the last video and go to the end and look and talk to hear me talk about that last point, but I'll say it real quick. If the charge is shooting something out that strikes other charges and pulls them in this case, then there comes a certain question, which is, well, if it's shooting entities out, wouldn't it eventually run out of these entities? Wouldn't it eventually run out of ammo, so to speak? And now there's two ways you can take this. You can say that, oh, well, these entities are a certain kind of entity that you can't run out of them. Now that would be, because we've never seen something that has unlimited entities that it can shoot out, it's very unlikely. Now, again, this is sort of loosely using the work of Ron Pizzaturo, but we have a lot of experience with entities, with the idea that entities are some kind of finite, are some sort of finite resource, and that can be depleted if they're continued to shot out. So on that basis, it's very unlikely that we are going to run into, it's not impossible, but it's unlikely. So what I find more likely is, do you remember the alternate to this, Mon? The alternate to entities shooting out of the charged object. What other physical effect might account for fields, these electric fields?
Fields are usually described as, like there is, like, how do I say this? Like electromagnetic, let's say light is a vibration in a field, right? So maybe these are not entities, but some sort of like disturbances traveling from two particles and now communicating.
Yeah, good. So the way, so I've been thinking about this for this thing you've brought up here. I've been thinking about it for a long time, and so I have some very carefully refined words to refer to what you've just said. I call this contiguous action through a medium. Okay? Contiguous, the word contiguous means that each object abuts each other object. It's like next to each other object. So for example, all of the United States except for Alaska and Hawaii are contiguous. All right? And this is opposed to continuous, which means basically the same thing but across time. So it's like it's there at each moment in time. So I call this contiguous action through a medium. So what is that? Well, basically, a more likely hypothesis for what's happening here is that there's an ether, and that the charge influences that ether in a way that spreads out at the speed of light. As we talked about before, these influences move at the speed of, changes in these influences move at the speed of light. Because they are light. Changes in these influences, as we get deeper into electromagnetism, if you didn't know it already, it turns out that if you change the electric field, you change the magnetic field too, and that is the same as light. That is a light pulse. That is constitutive of a light pulse, as Aristotle would say. So the charge doesn't need unlimited ammo because maybe it's influencing a medium, and those influences ripple outward at the speed of light. So whenever I talk about emanations, I could be talking about these projectiles, these entities shooting in every direction, but I could also be talking about contiguous action through a medium. So to understand this, we're going to talk about gravity real quick. Gravity, as we've discussed, the force of gravity, has a very similar form to the electromagnetic force. And we talked about last time how... not the electromagnetic, just the electric force, Q1, Q2, and then all of this. So we talked about how the similarities between these and how they're both indicative of spherical spreading, basically. This inverse square law is the result of spherical spreading. Okay, so Newton was aware of this. He was aware of this issue of spherical spreading, and so he probably also thought about the issue of unlimited ammo, and therefore rejected. And therefore, on that, I don't know this for sure, but Newton. Knowing the way Newton thought, he would have followed this same kind of reasoning. He would have rejected the idea of unlimited ammo. And here's what I do know for sure. In the queries, Newton makes an argument for the ether. Okay? Now, the queries are a special work by Newton, which basically, like, queries means questions, but I think maybe a better word for this work would be the hypotheses, because Newton puts forward a bunch of hypotheses about the underlying nature of light and gravitation. And I think other things, but I really have focused on light and gravitation when I read this work. So he puts forward the following hypothesis. First, he makes an argument for the ether, which I'll give that argument right now. If you have a glass vessel and you put a hot rod in it, okay, then the glass vessel will be warm to the touch. Okay, I can't draw a hand, not easily anyway. You don't want to sit here and watch me try to draw a hand. So if you touch the glass vessel, it's going to be hot. Why? Well, it's not hard to think of why. It's because the rod is heating up the air. The rod's heating up the air, which is heating up the glass. Then, if you suck the air out of the glass, and you keep the rod here, the glass still gets warm. So Newton says there must be something left in the glass that's transferring the heat. Now, it turns out that back then vacuums weren't that good. And Maxwell actually found out through calculations that a very, very, very thin distribution of air is actually still really good at conveying heat. So the actual cause of this conveyance of heat is not the ether, but it's the air. The air is still in the jar. But in Newton's context of knowledge, this was a pretty good argument for the ether. And we can substitute Huygens' argument instead, which is that light is a wave, but we can still see. I think it was Huygens who made this argument. I may be misattributing it, but basically, you can see the rod in there, and light's a wave, so there must be something left in the jar. That's the argument I made. I actually came up with that argument independently, and it turns out it's been made before in the history of physics, and it's an argument for the ether. Anyway, he's got this argument for the ether. Now, what's interesting is that this is a luminiferous ether. It's a ether pertaining to light. But Newton is going to take that and he's going to extend it to gravitation. My Californian douchey accent is coming through. So here was Newton's hypothesis. Newton says, what if near a planet or any heavy body, there's a low pressure area. So I'm drawing a bunch of L's which represent low pressure. Okay? Oops. And then I drew a 4 for some reason. Near two bodies, there's going to be low pressure in the ether. Okay? There's going to be low pressure in the ether. All right? Now, why does he hypothesize this? Well, there is an ether, number one, and he has a good argument for it in his own context of knowledge. We have an irrefutable argument in our context of knowledge, which is that of light. So here's the argument. These low pressure areas are all around, which means in between the two planets is a super low pressure, or maybe this is the Earth and the Moon. Between the Earth and the Moon is a super low pressure, so I put SL for super low. Now, this is regular low, so this is actually kind of high in comparison. And out here, again, it's kind of high in comparison to the super low in between. So what do you have here? You got high pressure pushing this way into the low pressure, and you got high pressure pushing this way into the low pressure. So in other words, planets attract one another. Perhaps, this is Newton's query, he asks, perhaps planets attract one another because they create these low pressure regions in the ether, and that causes them to attract. Okay? Does that make sense?
Yep.
Yeah, so this is a reasonable hypothesis. Now, what's interesting is he integrates this with the nature of light. He integrates this with the nature of light. So, Mon, mark this down. It's going to be 1715 or like 1710, because I need to look up the queries and make sure I'm getting something right. So this will just be a little break. Newton's queries. So, save your question for when we come back.
Okay.
Because you're gonna cut this, and so as soon as your question begins, that's when we will not cut it. That's when we'll pick back up. Let's see, optics. Come on, dude. Newton's queries. Okay, actually, I don't need to look up Newton's queries. I can just do this. Let's see. Fish. Light bending fish. Okay, here we go. So, light always penetrates more directly. Light always penetrates more directly. Or no, it's less directly. What? Yeah, light always penetrates more directly into the denser medium. Into the denser media. Okay. Okay, that's something I just needed to look up. So you can, Mon, go ahead and give a note that at 1845 we end the cut, and then go ahead and ask your question.
Okay. So what we're saying is that let's say these two are planets, and they're causing there to be a super low region between the two and the low regions around them. So are they like attracting attracting the ether towards themselves, so that there is this cause, like what's happening here? Can you
As far as I know, Newton didn't propose, this would have made his argument a heck of a lot stronger, but Newton didn't propose a mechanism by which the mass actually reduced the density of the ether in its vicinity. He didn't make such a claim, as far as I know. Yeah.
Okay. So.
Yeah.
So he's like, he said that this, we do not know how it does this, but if this is done, given that we know that there is an ether, which he gave the justification for, we know that, okay, if somehow this is the case, then this explains gravity. And then he the question of how.
Yeah, and he made a pretty strong argument, because he actually connects all of this to the nature of light. You'll notice that he connects this to the nature of light. So he actually proposes a whole theory wherein like light and gravity are integrated, basically, because they're phenomena of the same ether. And here's how he does that. What he does is he says, remember, it's low pressure here, and then maybe medium pressure here, and then high pressure out here. So there's a pressure gradient, in other words. And the word gradient is going to end up being really important for us in just a moment. So what he says is he says light bends. I'm sorry, waves change their direction when they move from one media to another.
Yep.
And what Newton says is he says, so as a result, light would, let's say you have light going like this, it's going to bend towards the planet like this. It's going to bend towards the planet. Now, you know what's funny is, now his evidence for this is that light bends when it moves from a denser medium to a less dense medium. And so he proposed the very reasonable hypothesis that this is what was happening. Now, by my reading, and I've read this a few times, by my reading, Newton made a mistake here, like as crazy as that sounds. Let's see. So let me show you what the mistake was. Basically, if he's right about the pressure gradient of the ether, or like, rather, the density gradient of the ether, if he's right about it in this way, then the light would not bend in this way. Because check this out. Let's say here's the water, here's a fish, and then here's you looking at it, okay? The light from the fish, let's see, what color, let's say the fish is green. Okay, the light from the fish does this, watch. So it goes like this, and then goes like this. Now, so what this means is that to put this, so this is water, and then this is air. To put this crudely, light bends away from the rarer medium. So you can see, light bends away from the rarer medium. So air is rarer, and so the light takes the less direct path once it reaches the air. Now check this out. So if that's the case, then what's going on with this light beam is that let's retrace this. At this stage, the light beam is kind of in general, it's pointing this way. It's pointing towards the denser medium. It would go like this.
Yeah.
It would bend towards the denser medium. So by my careful reading of this, Newton makes a mistake in my judgment in the queries. He has a good hypothesis, like this pressure gradient, that would make sense, but then he tries to integrate it with light and it doesn't make sense. So that's food for thought. It's worth noting that hypotheses that I've had on my channel regarding the ether, such as the waterfall hypothesis, the idea that planets are sucking the ether in, these also involve a density gradient. Can you think of what the density gradient is in this situation?
The opposite, right?
It's the opposite, and how do you know? Yeah.
Because the way that light actually bends, like the way you showed it earlier, which we have observed, like that would have, of course, like that lines up with this. And also, if something is pulling something in, then the closer you are to the thing, the more of that thing would be there. You can imagine a drain, right? A drain which is like pulling a lot of water in. The closer you are to the drain, the more water would be around, and the more you move away from the drain, the flow of the water would be lower.
Right. Okay, so that's kind of an analogy you use to remember the direction that light bends when it's going through differential densities, is this idea of a train, and part of the train goes faster, causing the train to turn.
No. I was saying something else.
Oh.
I was saying.
Oh, okay.
Let's take a sink, right? We have sinks in our bathrooms and stuff. If water is being drained and
Oh,
the more
drained.
yes, yes. So the closer you are to the, let's say, edge of the sink, the more water would be
Hmm.
there, and the more further away you move, especially the more water flow would be there. So like there is higher amount of water passing through that area, and like the more you move away, there's less. So if something is pulling stuff towards itself, there will be more stuff the closer you go to the thing. You know.
Yeah, good. The way to see one way to see that is that this ring of ether right here, let's say it has a certain density, it constitutes a certain volume. What would the volume of this be? It would be 4 pi r squared times dr, where dr is the thickness of that small ring. Okay?
Yes.
Then once that ring gets closer, the volume is now r, like let's call this r outer. Ro means r outer. The volume is, let's put a red box around that because it's going to be a red circle now. So the volume of this red shell is less. But it's the same amount of material because all of that stuff contracts in. So the density actually gets higher under this hypothesis, which is consistent with the direction that light in fact bends. And so now I've voiced other problems with this hypothesis, namely the idea that the ether is moving through space when space might be a property of the ether, but space isn't necessarily a property of the ether. It's possible that the ether really just moves through space. Now, the ether can't be the same as space, and I've argued with Henry about this. But this is a completely reasonable hypothesis if you think about the ether as a substance moving through space. Completely reasonable. And it's consistent with this. All right.
Yeah.
So getting back to this, so what's going on here? What we have here is a hypothesis that we don't have a vector field, actually. What we have is a scalar field. A scalar field, now what's a scalar field? Tell me the difference between a vector field and a scalar field.
Well, direction would be if the direction of the forces is unimportant, it would be a scalar field. And if it's important, then it's a vector field. So in gravitation, there won't be any repelling. So there is like the only one that there's only one direction that matters. That would be the attractive force. So we don't need vectors. We can define everything we need to define with that scalar.
We don't need vectors. We can define everything we need with scalars. Yeah. Specifically, what Newton is proposing here is that there's a pressure at each location, and you can think of that as a scalar at each location. So in the modern parlance, we call this a scalar field. Something with a number at each three-dimensional location. Okay, so, and I'm drawing this very roughly, and I'm not drawing a scalar at each location because I just don't want to take the time. But you can see, and the other thing is I've kind of reversed this. So let me, because I made the smaller object have the larger gradient. So I'll switch these so that the larger object has the larger gradient. So you can see that the number gets smaller the closer we get to this planet, and then the number gets smaller the closer we get to this moon. And then here's kind of like an equilibrium surface. I didn't draw the shape of the equilibrium surface quite right, but that's the idea. Now, let's draw this again, only we're going to draw the gravitational fields at each location. And I'm not going to draw all of them. This is a vector field. This is a vector field, okay? At each location, there's actually three numbers. At each location, there's three numbers. I didn't draw these large enough. These have to be at least as big as what's going on in the other one. What's going on near the other one. And these have to get bigger too. Yeah, there we go. That's better. All right, and then we have sort of this surface where there's no vectors at all. Yeah, rough, but it's capturing something. Low resolution picture, but a picture nonetheless. Okay, so at each location there's 3 numbers, and the 3 numbers, so to speak, represent the magnitude and direction of the force that could happen at that location. Okay, it's the magnitude and direction of the force that could happen at this location. Okay, now I got into an argument with someone, a debate, I should say, not like a disagreeable argument. I think it was Dan Harris. The guy the last guest I had on my program, who presented his theory of specificity. He gave a good argument against the idea of field. So what this is a gravitational field, right? It tells us the force that could happen at any given location. And Dan had a really good argument against this. He said, wait a second. The force doesn't happen unless there's actually an object at any one of these locations. Now, if there's a dude there, yeah, sure, there'll be a gravitational force on that dude. But if there isn't, there's no force. So does it even make sense to talk about there being any kind of real physical arrow at that location? Well, I shouldn't say physical arrow. Any kind of physical phenomena that has direction. Does that make any sense to talk about a physical phenomena that really has direction when that directional phenomena doesn't exist yet? You're talking about the potential for it to exist, but it doesn't exist yet. So, like, that it's fine as an abstraction, but making the claim that the field really physically exists somehow, that there's some kind of underlying directional existent at that location, you haven't proven that. What do you think of this argument, Mon? Do you agree? Do you have a counter argument?
Let me try to counter this in some way. So, well, even when there isn't an object there, something is causing the force, right? And
but when there's no object there, there's no force.
But okay, when let's say there is an object, right? Now that object experiences a force towards the other object.
Yep.
It cannot be just action at a distance for no reason. There is some underlying physical reason there. And I think that has to be represented somehow. And as we were just discussing, it could be simply the ether being pulled into something, and that creates a potential difference between the two ethers, I guess. And that causes something like that. But we cannot just leave it at that okay, this is just an abstract way of telling us what happens when there is a force. When we cannot just leave the question of why is there a force unanswered. And those arrows, they are representing something physical causing this. An arrow is like a causative, symbol. So there is is something which is causing it.
Yeah, it represents some kind of phenomena with direction. Okay. Now, let me give you my opinion on some of what you just said. I don't think there's anything fundamentally wrong with action at a distance. I don't think it violates the law of identity or violates any fundamental rule. You're in good company, though. Newton agrees with you on this point. Newton says, if you think one object, this is like a paraphrasing. He basically says, if you think one object can act on another object at a distance without influencing entities in between, it means you need a better physics education. You need to be educated more in physics. Okay, so now, I don't think that's an argument. I basically just say, why not? Why can't it act at a distance? Okay, here's the thing, though. We don't need to make a specious or argument like this in order to know that the action is local. The reason is because with, at least in the modern day at least, we have a luxury Newton didn't have. We know that the changes in the electric field and the changes in the gravitational field, we know they propagate at the speed of light. We know they spread spherically outward and that they take a certain amount of time to spread for their influence to change. So we know it's not acting at a distance. We know it's here, then it's here, then it's here, then it's... We know it's not acting at a distance. Okay, now, so I really think that my view is that we don't take Newton's argument, we take the argument I just gave. That's the argument we use to know that there really is that there is no action at a distance. Okay. So it's not that it's like metaphysically impossible, it's just that the evidence shows us that it's local action. It's this spreading action that happens at the location of where the ether is being influenced there. Okay, now, getting to your other point. What was your other point? Okay, I'm going to make another argument. Dan made this argument. This arrow only represents a potential. I hear what you're saying, but this arrow only represents a potential. This arrow only happens as a result of a body being at this location in addition to whatever's here. So yeah, there might be something there, but the thing that's there doesn't have direction, because that directional thing, the force, only comes into being when there's some body there. So you don't get to attribute this directional thing to that location or that part of the ether.
I don't think that's a proper argument.
Okay, why not? I don't either.
Yeah, because a lot, it echoes of, the intrinsic subjective objective dichotomy, right? That a phenomena exists connected to another phenomena does not invalidate that, right? So sure, like that other object has to be there for the arrow to make sense. We are only using the arrow in the context of the other object, but that does not mean that arrow is like, that does not mean that the thing that the arrow represents does not exist. It is a dependent phenomena of the object in some way. The object is somehow connected to the phenomena, but that does not invalidate.
Yeah, I agree with your argument. I stated a little bit differently. The way I put it is, yeah, it's true that this arrow this is really similar to what you're saying. It's true that the arrow can only exist once there's a body there, but what that means is that the arrow depends on some property of the body and some property of the ether at that location, which means that the property of the ether at that location still has directionality. Now, our only grasp of this property of the ether, whatever the heck it is, our only grasp of it is the force that it could produce at that location. But nonetheless, it must have some directional property at that location that is more than just the force, because it is part of the cause of that force. It's only part of the cause, you're right, Dan, but it's part of the cause, so it has direction. Yeah. Okay, so yeah, now, this is a great segue, because now we can get into what Newton thought the cause of these arrows was in gravitational fields. Okay, so what did Newton think? So Newton basically thought, getting back to this, Newton thought that, we can write these these vector fields. Let me get rid of the extra stuff. We can write these vector fields, or we can write a scalar field. The scalar field being the density distribution. And what the vector fields are just a bunch of arrows pointing. They're gradients. They're arrows that point, and they're negative gradients. They point from the higher density regions to the lower density regions. Okay? And what does that look like? It looks the friggin' same as this vector field, it is that vector field. And so what does that give us? This gives us an equation. Now, all of this, so what are these gravitational field lines? What they're really telling us is what they really might be telling us is just the ether density gradient, the direction of decreasing ether pressure.
Yep.
Okay? Now, we can take all of these arguments and apply them. So we've been talking about gravity, but we can take all of these arguments and apply them to the electric field. Apply them to the electric field. The electric force at each location is equal to the electric field at that location times the charge. Okay? So, in other words, there's this property of the ether, and then there's Q, the property of the object being affected by the ether. And the amount of charge that an object has is telling us how much the ether affects it. Okay? Now, what we can do is we can talk about a scalar. Instead of thinking of this as a vector field, we can think about the following scalar field. And of course, I'm sure this equation is not new to many of you. I mean, like, incidentally, for people in the audience, if you haven't seen this equation before, if you've just never seen it, if you have to look it up to like remember what it means or whatever, then that's fine. But if you've really never seen the equation, then this series is probably a little bit over your head. This series is really meant for people who have taken a college level physics course on this, or maybe a very advanced high school physics course. I don't know, I think a lot of what we've just said is actually going to be pretty accessible to people who don't know this math, but ideally you would know this math. Okay, but anyway, so this is the negative gradient. So in other words, the electric field is the negative gradient of a certain scalar field. Now take a look. What we're saying is, notice how I put a bar on this boy. That just means it's a vector field. So there's E is a vector. It's a vector that's defined at each location R bar. R bar just basically means X, Y, Z. Okay, it just means any given location. Now, V is a scalar field, which means there's a number defined at each location R. And then this upside down triangle is here because that is a sort of directional derivative. Okay, now let me write out what this means for anyone forgetting the detailed meaning of this. So I'll write this out. So now so I've covered the physical hypothesis that motivates this. And you know what's interesting is that if you've ever taken a lecture on this, just to remind you, the way that this is called the electric potential or the voltage. And it is usually motivated through the concept of potential energy. You'll notice that what I have done is I've motivated it through a hypothesis of what the ether is doing. I have this completely different motivation. V would be a kind of electric pressure. Now, by the way, it's probably not the case that it's this simple, okay? Just so you know. But based on how much we've covered in electromagnetism so far in this series, this is a completely reasonable hypothesis. Okay, basically, it's like guaranteed to not be this simple, because the electric field can curl. The electric field can curl in on itself, and you can't have a pressure gradient that curls in on itself. That turns out to make no sense. We're going to cover that later. Actually, we might cover that later today. But yeah, so let's talk about what this means. This is a gradient. So I'm taking the derivatives. I'm taking the derivatives in a certain funky way. Let's talk about what this means. Now, actually, let me ask you something. Mon, why don't you tell me the physical meaning you ascribe to this equation?
Okay. Well, this means that the electric field is the gradient, like the how do I put this? We know that it's associated with potential difference, right? So it is the difference between 2 points and their potentials. That's going to be proportional to the pull of the electric field in that region. And this is how we determine. Uh, I think, like I'm coming at, I usually come at all of this from a very, like experimental point of view. So, like, the way I'm imagining is there is a charged particle here and it's moving from A to B. And why is it doing this? And then we have the knowledge of electric fields. So there must be some difference between point A and point B. So that point B is preferable. There is like something that pulls it, as you said, a pressure towards point B. And this is what defines that pressure. It's a negative gradient. That means that it goes towards that point. Basically, like, negative gives the direction of going towards where the pull is. So yeah, I think I would.
Yeah.
This is number one.
So yeah, the negative means it's going towards the area of lower pressure, and that's true for positive charges. Positive charges are pushed towards the area of higher pressure. Positive charges are pushed towards the area of lower pressure. Negative charges are pushed towards the area of higher pressure, is what this would be. What I was specifically asking, though, is what does this mean mathematically? Like, how does this give an arrow exactly? Let me show you how. Let's say you have a charge. What's that?
That's that's how we represent a vector, right? And like
Yeah.
there is some
Yeah, I
component
mean,
that
so
is
yeah,
not
these
zero.
parts represent IJK's, the X component, Y component, Z component.
Mhm. Okay, and it shows the gradient in all three directions. So if we know that, we know where it's going.
Oops. Um, yeah. Um, well, the gradient is supposed, let me ask the question of you this way. The gradient is supposed to tell us the direction and magnitude of greatest increase in the scalar field. How does this set of greatest decrease, because it's the negative gradient right now that makes it direction of greatest decrease. How is it that this mathematical operation gives us that direction of greatest decrease? How does it do that with these derivatives and these vectors?
Uh, well, the scalar field has, uh, you know, like every successive point has a different number, and where the next number has to be can be, represented by a vector, a very small, let's say, vector, unit vector, assuming that we are moving one unit at a time, and that needs a certain, you know, directional component. Where is, like, the question is, where is the next smallest scalar point that we can jump to, so that the particle has, you know, it moves along to the lowest possible.
How satisfied are you with your answer?
6 out of
What's that?
6 out of 10.
6 out of 10? Okay. Yeah. A lot of times I ask this of my students to see what kind of like clarification it gives to you to give your own answer like this. So I've been working on this for quite a while. So why do I keep drawing H instead of 10? It's like a mental disorder. So I've been working on this for a while. So here's the way I've come to think about it. Let's see. Let me think here. So we have these gradients, and the vectors are supposed to point along the line of decrease. How does this really achieve that, though? That's the question we're trying to answer. Let me show you. Let's say you're at this location. Okay, let's say you're at this location. And let's say at your location, the scalar field, at your location, let's say the scalar field has a value of 5. I've made the head really big so that so that we can write the value of the scalar field at that location. All right. So, and then let's say, actually, let's make it 15. Okay. Then let's say in this direction, there's a 13. In this direction, there's a 10. Okay. And then in this direction, there is a 20. And then over here, there's an 18. Okay. Now check this out. That means as you move this direction, now I'm speaking very crudely here, but there's a -3 change in pressure for every change in x. Okay? I'm being very crude. I'm treating the change in x as like one single unit. Now, when you take a limit, you always end up doing that, though. So this actually isn't as crude as it sounds, but I'm not bothering with the limit perspective, the differential tiny increment perspective. I'm just not thinking about that right now because it adds extra complication, makes this all just harder to understand. Then in this direction, the change is -5. Okay, so what is that going to do? Now, we're dealing with a two-dimensional case here, so we're just not going to worry about the z direction. But the z direction is simple once you understand the other two directions. So what's going to happen here? What's going to happen is that the gradient is -3 in this direction, and it's -5 in this direction. Now, what's that going to do? That's going to create a gradient which points in this direction. Now notice it favors the y direction. It's not at a let's make it favor it a little bit more just to make it clear. So the idea is that because you're taking a small step down in this direction and a smaller step down in the y direction, your vector at this point, what's the vector at this point going to be? So as I was saying, whatever number, it assigns a -3 to x, and it assigns a -5 to y, and that gives us a direction. Okay, that gives us a direction. Now, by the way, real quick, because it's the negative of a negative, then this ends up being positive, and this ends up being positive, which is why we have a vector pointing in the upper right quadrant. Okay, so it allocates those different quantities to the different components, and the end result of that is that the vector ends up pointing in the direction of greatest decrease. That's what ends up happening. Okay, so that's how the math actually leads to pointing in the direction of greatest decrease. Now, are you feeling more comfortable with the meaning of the math now, or do you have anything that any clarifications you still need?
No, I understand this. This is just how vectors work, right?
Well, I mean, the part where, we got 5 in one direction, 3 in the other, that's just how vectors work. Yeah. But specifically, it's that the change the change in the scalar field when you move in the x direction, that is allocated to the x component of the vector. And the change in the change in the scalar field when you move in the y direction, that is allocated to the y component of the vector field. And as a result, these two things, when you combine them, create a vector that preferentially points in the steeper direction, and thus what it does is it gives you the direction of greatest decrease as a result of that. It preferentially points based on the decreases in these different directions. Yeah. So that's what that does. So that's a gradient. So here's the way to think about this. We think of the electric field as a vector field. But really, all of the information, so to speak, all of the identity that's in the electric field might really just be wrapped up in a scalar field. And so the vector field is just kind of a derivative phenomena. The essential might be some kind of scalar field. Now, we don't know what the ether is really doing, and there's a lot more to electromagnetism that we haven't integrated. But based on what we've understood so far, we validly entertain the hypothesis that the electric field is completely caused by some scalar field. Okay? Now, the scalar field is called the electric potential. I don't like this word. I don't like this because it's based on potential energy. That's why it's called a potential. But it isn't potential energy. It's related to potential energy, of course, because you can find the electric potential energy through this formula. And so as a result, there's a mathematical, there's a mathematical parallel here. What's the parallel? The electric force, go ahead.
Go ahead.
The electric force is based on the electric field at a certain location in the ether, multiplied by the charge of the object at that location. And similarly, the potential energy is equal to the voltage, or electric potential, times the Q. I like to call V voltage because it avoids calling it an electric potential, which I find to be confusing. Because I get it, it's related to potential energy, but I prefer to think of it as its own independent property of the ether. Now later, you may know that in electrodynamics, we stop thinking about voltage per se, and we start thinking about, we tend to use phi, which is one of the four potentials. Have you ever heard of the electromagnetic four potentials, or the vector potential? It's phi and A. Have you studied this before?
I've heard of it. I have studied it. But it's been a long time. I basically don't know.
Yeah.
I'll revise it and get it done. So
I think you may want to put your efforts elsewhere. You don't need to review or revise it. In America, we don't use the word revise in that way. When we think of revise, we think of like rewriting something. But yeah, I know in the Anglo-Saxon world, that's how they use the word. Yeah, just for anyone who isn't aware, revise means review in the Anglo-Saxon usage. Yeah. You don't need to review that because we're gonna go over it. It's cool though. It's cool. So if you take a few minutes to review, it's not a priority in case you have other priorities. So, So this ends up being the scalar potential that we end up focusing on, which is not quite the same as voltage, because it involves situations where the electric charges are moving, basically, or where electric charges are moving and where the currents are changing over time. But for now, that's good. Let's see, what else are we going to cover? So what I've done is I've taken this concept of electric potential and I've taught it in a very different order than it's usually taught, I've focused on the possible physical meaning of this concept, of this number. I've focused on its possible physical meaning. Now, we don't know if this is its real physical meaning. This is just a hypothesis that I've put forward regarding pressure. So, yeah, so keep that in mind. This is just a hypothesis about, regarding pressure. So, but I've started with that, which could have been the motivation, and it ends up being this kind of ether parallel to the potential energy, just as electric field is an ether parallel to the force. Let me go into that in a little more detail.
Yeah.
I'm going to write, let's see. I'm going to write a couple of equations. I'm going to arrange this in a certain way. So we're going to put the electric field stuff on the left, and we're going to put voltage stuff on the right. So the electric field caused by a single charge, and this is all going to be review, but we're going to take all this stuff we already know and we're going to look at it from a certain perspective, the perspective of broad physical categories. Oops, I added an additional Q there when I didn't need to. R hat squared, okay, and then this is potential. No, we want voltage, a different R, E, a different R. Okay, Q1, Okay, and I'm going to look something up because I want to make sure. I always forget a negative sign here. Oh, I don't need to look this up. I actually have a way of checking this in my head. I've written it correctly. Yeah, and Google agrees with me. So, okay, so here's the deal. I'm going to give you a perspective on, so this is the electric field perspective. This is the scalar field perspective, okay? All right, and these are two perspectives which, in the case of electrostatics, where the charges aren't moving and the currents aren't changing with time, from the perspective of electrostatics, these perspectives are just completely equivalent, okay? Because why? I'll show you the equation. There's an equation that links the two. E is just the gradient of V, okay? And so I'm going to put that in the middle to show it links the two perspectives. All right, what are the perspectives? Let me go in order. First, we got this equation, and this equation tells us the effect that a charged particle has on the ether. Because look at this. It's the electric field vector at each location, ... all of these nearby locations near the charge. So what this equation tells us is it tells us how does the charge affect the ether, okay? Now, to get into my broad physical categories, you can watch my video, for my audience, you can watch my video on broad physical categories that gets into these concepts that are really helpful in making inferences in science. According to the broad physical categories, this equation tells us the sense in which charge is a efficient cause. Okay? What do I mean by an efficient cause? An efficient cause is a property of an entity which causes it to act in a certain way. This is the active characteristic of charge. It tells us that charge is this aspect of an entity which tells us how it affects the ether, right? Because like the bigger this number is, the more effect it has on the ether, okay? Now, conversely, charge is also a passive cause. it's also a passion. Okay, now by passion I don't mean that it's, the charge is just like super emotional. I'm using passion in the way it's attributed to Aristotle, at least in the English translations. And that's to say, a passion is a characteristic of an entity that tells us how it can be acted upon. Okay? And that comes into play in this second equation. So if there's an electric field, E, and it acts on a charge with charge Q, then a resulting force is going to happen. Now, I've said a bunch of stuff just now that's like obvious, but my point is not to re-educate you in the obvious equation. My point is to give you a certain perspective on it, which is that this is the cause, this is the passion, and this is the resulting effect. What is a passion again? It's the susceptibility of the object to receiving a certain kind of action. The ether has this property. What is this property? It means the ether has some kind of directional property at that location. We have no idea what it is, but we have to use exact language like this and make inferences from this exact language if we want to be able to infer what the hell is actually going on. So the ether, it's got some kind of property, and we call it the electric field. That electric field acts on the object. How hard does it act on the object? Well, it depends on how passionate the object is, how much charge it has. And however much charge there is and however active the ether is, that's how much force is applied to the object. All right? So this kind of language, framing it this way, it leads us to very interesting conclusions. Here's something important. This tells us that charge is a separate property of the entity. What do I mean by that? Charge is not just its active characteristic, and it's not just its passion. It's a separate property that influences both. There's three aspects to charge. We know that there's three aspects to charge here. How do we know? Because there's the active aspect, the passive aspect, and there's the link between them, which shows that charge is this independent aspect of the entity. It's an independent aspect of the entity that leads to both of these other things. Okay, so this is an example of how broad physical categories allows us to take these baby steps towards, and then sometimes giant leaps, but this is a baby step that I've presented to you today. The baby step, once again, is that the charge it's not a fundamental characteristic. Well, it might be a fundamental characteristic, but the active quality is not a fundamental characteristic. The passive quality is not a fundamental characteristic. They both rely on an inner characteristic, the charge. I need to think of better language for this stuff, but this is the kind of thing that broad physical categories allows us to probe into. Your face has questions.
No. I'm just trying to understand. We can say that charge is a fundamental intrinsic quality in a particular substance, particular entity, which causes both the active and the passive characteristics, the causative
Yes.
Efficient cause and the passion used.
Yes. But I would amend one thing about what you said. It's fundamental in our current context of knowledge. We don't know what further characteristics give rise to charge. If any, it could be fundamental. This could be the bottom of reality, or an element of the bottom of reality, that bodies just have charge or they don't, and there's nothing more to it. That could be the case. But we can see that whatever this property is, charge, it gives rise to both the passive and active qualities. Okay, now let's turn to potential, electric potential or voltage. This is telling us how the charged object affects the ether around it, but from this voltage perspective, or maybe the pressure perspective. It tells us that the further out you get from a positive object, the lower the pressure gets, basically. One thing that's a little bit awkward here is that if this is a negative number, it leads to negative pressures in the vicinity, which is kind of awkward. And so, but there's a sense, but here's the way you could put it. Basically, you could say we don't know what the minimum pressure is for the ether, maybe. And when we call something a negative pressure, that's just us choosing whenever we say that something's zero pressure, we're just choosing that as a reference point. Like when we measure literal pressures of air, we tend to use atmospheric pressure as zero. I think that's called gauge pressure when we set atmospheric pressure at zero. And you'll notice that if you think about the way voltage is used in electrodynamics or in electrostatics, you'll remember that where you set the 0 point is up to you. The experiments and the evidence do not constrain us to setting the 0 point at some particular location. There are more convenient settings than others, like setting some point that's infinitely far away from all charges, setting that to 0. That tends to be convenient. But when you do that, you end up with negative pressures still, because you're infinitely far away from the negative charges and from the positive charges, so it equals out. If you're near a negative charge, you're still going to get negative pressure, which is weird, like I said. But maybe it's just a matter of perspective, or more likely, the pressure hypothesis probably just isn't sufficient to really describe what the ether is doing. That's probably the case. So this is telling us how the ether influences the pressure around it. Pressure in quotes, because I don't know if it's pressure. Then this is telling us... Go ahead.
I think perhaps this might be helpful. A pressure, when we imagine a pressure, it is a pushing force, right? So a negative pressure would simply be a pulling force, wouldn't it?
We should really get into, kind of, but really we should get into what we're talking about when we're talking about pressure, okay? We should talk about that. So when let's forget about voltage for a moment, and let's literally just describe a pressure field. It's a scalar, okay? It's a scalar. All right. Let's see. What does that field represent? It represents the amount of outward pushing at each location. It represents the amount of outward pushing at each location, okay? And that pushing is newtons per square meter, okay?
Yep.
Now, if you have negative, so this is positive pressure. If you have negative pressure, that means that that location actually actively sucks things in, okay?
Yes.
Now let's say you have let's say that you have an object taking a journey from one location to another. So we'll make this, so I'll draw some 6, 4, 2, 0, okay? Let's say that an object is pushed along a tube in a fluid. Let's say this is all a fluid and the different parts of the fluid have different pressures, okay? And this object is pushed along this gradient. Then what does this look like? Well, what it looks like is that we have a pressure, the pressure field dot dr, okay? And I'm not getting the units quite right. If you look at this, then you'll notice that my units are not, this doesn't come out to, Actually, does it? It might. So it's pressure.dr, and what this does is it tells you the change in energy. This is work. This is work. Okay. Now I think what we need to do. So I think here's like I said, I didn't get my units right because I'm not fully conceptually getting this. I think it's like this. Okay, so what's going on here? First, there's a pressure at each location, and the pressure, there's a pressure at each location, and we're multiplying that pressure by area, because remember, pressure is force divided by area. Okay, the way to, in case anyone is a little hazy on pressure, and it'll help, or even if you feel like you understand pressure pretty well, it's going to help you to understand this explanation. Consider taking a pistol and firing the pistol, okay? And you shoot it at a wall, okay? And the bullet blows a hole in the wall. Which object suffered more force, the wall or your hand? Do you know the answer?
Well, the force must be equal because...
Yeah, it's actually the wall because the bullet slows down a little bit before hitting the wall. But the force...
But assuming that's not the case, like assuming here is the...
Right. Yeah, it's basic. Now, here's what's funny. The wall got a hole punched through it. How did you not end up with a hole punched through your hand?
Because the bullet impacted a very small area versus the hand is a much bigger area.
Yeah. So you got this 9mm circle where all of the force was focused versus the distribution over your whole hand. Okay, so and that makes a huge difference. Like, I mean, shooting a gun is not too uncomfortable of an experience. My girlfriend, who's Canadian, I had her shoot a gun for the first time, and she shot it. She shot a big rifle, and she's like, "Oh, it's not that bad." She was expecting just like boom, and she discovered it wasn't that bad. It was just boom. Okay, yeah, that's all. That's it. It's about the same as like, I don't know, like a 5-year-old punching you, something like that. As a 5-year-old punching you as hard as he can. It's about that much. So it's not much. And that punch is distributed over your whole hand or like a pretty large part of your shoulder. So anyway, so what we do here in this integral is we take the pressure and we multiply by the area, which is the cross-sectional area of this object. And that gives us a force. So this is force times distance, which is work. Okay. Yeah. Now, let me think a little further about this. What matters for this is the difference in pressure. It's the change in pressure that matters. So let's say we integrate from R1 to R2. Okay? R1 to R2. Well, then the pressure only changes from 10 to 6, as you can see from my primitive diagram. If you integrate this far, basically what's going on is there's a pressure of 10 pushing you this way, and then at the end, well, it's a pressure of 10 pushing you in both directions, but then at the end, you keep moving to an area where the pressure is smaller and smaller. And so that movement makes it so that you have less pressure pushing you at this position, and the work ends up being related to the difference in pressure. Let me tell you, I'm not fully happy with how I'm explaining this. I would like to, I should have prepared this a little bit more. I didn't even realize I'd be explaining this, but so I guess it's okay I didn't prepare. But really, I would like a better explanation of this in terms of the real cause and effect relationships. I've moved closer to that. Where, let me try it. Let me try this one more time. So we have a pressure here of P1, But then, what's interesting is we also have the pressure is pretty much going both ways. Like P1 is squeezing it from both directions. That being said, the pressure is going to be a little less on one side than on the other. So I'm trying to think of this. So maybe it's like, yeah. What's that?
Take a cube of unit area, and there's a 10 newtons force in this direction and a 6 newtons force in this direction. So it eventually moves over that.
What's interesting is I have a feeling that this isn't the pressure. It's the gradient. It may be the gradient in the pressure. Now, let me. So we've moved into an area that I'm not 100% qualified to lecture on because I didn't prepare for it. But let me tell you here. There's value that you and the audience can still get from this. I want to tell you. You're seeing me think about this live without preparation, and you're seeing that I'm approaching this all in a certain way. I'm saying I need to understand exactly the cause and effect relationships that make this integral what it is, and make this integral an identification of the work. And you can see I've made some steps towards that, but some of them are probably wrong. And you might say, oh, well, what's the help in giving us a wrong lecture, James? Well, ideally I would have given you a right lecture, but you're seeing the process here. You're seeing the process of how you break this down and how you try to fully understand this physically. And then lastly, you're understanding what it looks like when I'm not satisfied. And I think you can see there's real epistemic standards that I haven't met here. And so by showing you that I haven't met them, there's other times in these lectures where I have met them, but now you're seeing a place where I haven't, where I'm somewhat satisfied. I know that there's some kind of integral like this. And for the sake of time, let's move on. And I mean, a full explanation of this is going to have to wait for my induction of this, when I make a rigorous induction of this eventually. But you'll remember that if we have an electric field and we integrate over dr, what is this? That's a change in voltage. That gives you, when you integrate from one location to another location. And so and you'll recognize this as just one of the equations of the class. Let me make sure I made my negative signs properly. Let's make sure I did my negative signs properly. Yes, I did. Yes, I did. Okay, yeah, I'm seeing it in Griffiths. So, you can see that there are real similarities between this and pressure, basically. Okay? And incidentally, when Maxwell first theoretically tried to understand electrostatics, he viewed this as fluid flowing as a result of differential pressures. He thought of the fluid just flowing through and that the fluid was encountering resistance as it moved. It was a fluid model of the ether. Okay? And so we can see that has left that continues to be a plausible hypothesis if we confine ourselves to electrostatics only. If we start looking at further things, then we find that this view of pressure, it's not enough to account for the other electromagnetic phenomena. All right, any questions on that before I move on?
No, but I can add to your statement in one way, which can be that even if there are errors in the results that someone is getting, I think the method of thinking matters more. So sometimes stuff like this where we venture into territory where you're not yet sure, but you're almost there, I think that can be very valuable to the audience as well, because they have a glimpse into the method, much more than just the content.
Yes. When I get it right, you're going to focus on the content a lot. But here, where the content is dubious, You can see the method that's leading to that content. That's really one of my goals. So yeah, that's well said. Yeah, okay. So now we're looking at Poisson's equation. So one way to think about this is we've already let's see, we've already done Gauss's law. Have I gone over the divergence theorem with you? Or wait, Gauss's law is the divergence theorem. Have we covered the meaning of divergence yet? Did we cover that last time?
We covered.
I think
pretty extensive.
I'll cover it real quick. Basically, we covered this, right?
Yep.
Yeah. What's that?
We talked about like the density of dielectrics a little bit, but I don't think we went further.
Okay, let's do this. This is the divergence. So we should have gone. It would have been more organized to go over this last time, but we're going to go over this real quick. So what is this saying? This is saying the same thing as Gauss's law, but it's saying it from a different perspective. Okay, what we have here is a vector field of electric field. Then here we have a scalar field, rho. The scalar field is the charge density at each location. So it's telling you which part of the ether has how much charge in it. In most locations, it's 0. Now how does this work? What it's saying is that so first of all, let's think about what divergence means. Okay, now this is interesting because divergence looks a lot like gradient, right? But it's different. It's not the same. Because here's what's going on. What's going on with divergence is that del, this upside down triangle, is the x derivative pointed in the x direction plus the y derivative. These should be partial derivatives. Hold on. There. The y derivative pointed in the y direction and the z derivative pointed in the z direction. Then we're dot producting that with ex in the x direction, ey in the y direction, and ez in the z direction. Okay? Once you do that dot product, look at what you get. You get dex dx with no direction. It's a scalar. These two vectors dot together to make a scalar. Dey in the y. A lot of people are probably really familiar with this, but I'm about to give the physical meaning. The juicy part is coming up. All right, so what does this mean? What does this all mean? Well, what this does is let's consider these 5 pieces of ether. There's a piece of ether in the center, and then there's pieces of ether on the sides, okay? Now, let's say there's an ex here, and let's say there's an ey here, okay? Now, when we take a step in the x direction, let us say that the ex grows stronger and that the ey stays the same, okay? Then when we take a step in the ey direction, the ey grows stronger and the ex grows the same. All right, now, let's say if we take a backward step, then the ex grows weaker and the ey stays the same. Okay? Then as we go down, the ey gets weaker and the ex stays the same. All right? Now, watch what's going to happen here. If dx is positive, that means we're taking a step to the right. Then the dex is going to get bigger. So that means this is positive. If, and this is a two-dimensional example, so we're not going to worry about the z direction. Okay, so and the z direction is trivial once you understand the two directions. If you take a step backwards, if this is negative, then you'll notice that this is also negative. The dex is negative. That's an x. All right, you see that? Okay.
Yep.
So in the situation I happen to draw here, this is a positive number, okay? It's positive whether you're going forwards or backwards. If it was positive in one direction and negative in the other, it would actually be zero. It would actually be zero because it shows that you've reached a point, you've reached a local max basically for the electric field in that direction, because it's negative in one direction, positive in the other, so in the middle it's zero. There's no change in the middle. All right, now similarly, EY grows larger when you take a step up and smaller when you take a step down. So if this is positive, the whole thing's positive. If this is negative, then this is negative, and the whole thing is, once again, in the way I happen to draw it here, the whole thing's positive. Now, what this means, according to this equation, is that we have a positive charge density at our central location in the ether. All right, now, what the heck does that mean? Well, in this situation, let me show you something. We had this background ambient field. This field is the field that exists at the location of the charge. Okay, what I'm going to do is I'm going to make this thing green to represent the fact that there's charge at that location. Okay, this charge existed as an ambient charge. Okay, then look at what happened. On this side, it made the electric field larger. It made the electric field in the X larger. On this side, it made the electric field in the Y larger. Okay, now watch this. On this side, the electric field was made smaller. What does that mean? That means this green location was producing electric emanations going to the left that reduced the ambient field. Because remember, the ambient field was already going like this. I drew an ambient field in order to make a point. Then the ambient field in the Y got smaller at this location. So what is this saying? It's saying, what is this equation saying? Let's bring it down so you can look at the picture while also looking at the equation. It's saying, so first of all, divergence. What does this mean? 3 blue 1 brown has said, and this is really good, it's the sourciness of a given location. How much extra field is generated by that location? And obviously, the amount of field generated by a given location is proportional to the charge density. This is the same thing as Gauss's law, because all Gauss's law does is it draws some kind of Gaussian surface around some object, and then it says the amount of emanations that penetrate the surface is equal to the amount of charge on the inside. Here, we say the amount of emanations, it's basically the same thing. It's just saying the amount of emanations that penetrate through some infinitesimal piece of the ether is proportional to the amount of charge inside that piece of ether. With Gauss's law, we're allowed to think of a Gaussian surface that's as large as we want, that contains as many ether pieces. And you'll notice it has the same look at it, it's the same form. It's the same form. This is just the flux through a tiny piece of the ether, through all of the different sides. It's not exactly it is the flux, but there's another perspective I'm adding to this. It is the total flux, but it's also the additional field lines. And that is characterized by these derivatives. Why? Because these derivatives tell you how the EX and the EY change from location to location. And when you add these different things up, what does it give you at the end? It gives you the additional field that's spewing forth from that location.
Yes.
Alrighty. Is this making sense?
Yep.
Okay, cool.
Basically,
good. Basically, where do you need further clarification? Your questions are going to be helpful to the audience because they're going to be having the same questions.
basically the center. Uh, it is like, by this equation we can differentiate, like we can find out uh, the nature of the source at the center, uh, as opposed to just what the ambient field is. Like they're differentiating the ambient field and the source at the center. So
Yes. And by adding these differentials, we are just talking about what is added to the ambient field. I have included an ambient field that happens to go this way, and that field gets canceled over here, and it gets added to here and here, and the net result is to say that this kind of additional field spews forth from this location. That's why I included an ambient field. That might be a little confusing. I usually don't present it in quite that order. Wasn't ideal order of presentation, but hopefully you can Tarantino it together at the end. Yeah. Okay, now, so so we've now explained divergence. Copy. All right. Okay. All right, now, only I'm going to put this here. We've already talked about how the electric field is equal to the gradient of the voltage. Okay, so here's the deal. If you take this equation and then you take the divergence of both sides, let's look at what you get. So I'm gonna take this equation. That's what I'm gonna do. I'm gonna copy this equation. Copy. I'm going to take the divergence of both sides. Now I'm allowed to do that because this is obviously a vector field, so I can take its divergence. And this is a vector field too because it's the gradient of a scalar field. So this whole thing is actually a vector. I take the divergence of both sides. Let's see what happens. E equals, okay, and then this turns out to be a whole new operator. It's a whole new operator, which is del squared, which is a little funny. This operator is a scalar. Wait, let me make sure I'm saying that right. Yeah, it is. It's a scalar. Why? Because you're taking the divergence of the divergence, or I'm sorry, you're dot producting del with itself. So what does that look like? It looks like this, and then it looks like this. So you dot product these two sons of guns, and so as a result, it's d squared dx of v. I'm just going to write this, and it's negative, so I'm just writing this down, plus dv dy. And once again, this is probably not news to most of you, although maybe some of the particular interpretation is, but more interpretation is coming up, I promise. So that's what this means right here. And then, thanks to the divergence theorem, we can just insert this right here. Okay, so this is equal to the density. Copy. So check this out. The negative second derivative is equal to the density. Okay. Now, what is the second? So the negative, it's more like this. The negative 3D second derivative is equal to density. All right, that's going to be a little tough to abstractly wrap our heads around, but let's try it. First of all, we're going to ask, what does a regular second derivative represent? Let's think about that. If you think about it this way, it ends up being a lot easier. So I'm going to draw a sine wave. So check this out. The second derivative tells us whether it's concave up or concave down. It's the change in the change. Now, the second derivative I've said in a previous video, it's the change in the change, okay? But really, like, so let's see. Do I want to do I want to explain this completely? I don't. Y'all can go to, what's the name of the video? Are electric and magnetic fields real? In that video, I explain in painstaking detail what a second derivative means. For now, I'm gonna just call it concavity, okay? I mean, and that's valid, but that's a summary. It's not exactly telling you, what it means. But here's the deal. And I can say it real quick, actually. I can say this real quick. Look at the slope here. The slope at this location is negative. Then the slope at this location is 0. Then the slope at this location is positive. So if we think of the change in the slope as we proceed in the x direction, then watch what happens. It goes from negative, then 0, then positive. It's going up. This is a region of positive concavity, which is a little bit funny because it's dipping down. But when it dips down, that's called positive concavity, okay? And for the same kind of reason, it's positive, then 0, then negative. This is a region of negative concavity. The explanation I give in the other video is better, but it takes a long time. So I'm going to do it quick here. So you can get into more detail by watching that other video. But for now, I'm just referring to concavity. Now, so what's going on here? This up here is negative 3D concavity. Now, what the hell does that mean? Now, I've worked this out, and here's what it means. Imagine that we have, and it's the concavity of V, by the way, okay? Now, what I'm going to do is I'm going to draw V as a density gradient. Watch this. I've done my best here to make a high density at the center and a density that slowly decreases as we go. My medium density is dubious, but you can see it's high density here, medium density here, and then low density out here. That's what I was going for. You can kind of see it, okay? All right, what does that mean? Well, if we were to draw this in one dimension, this would look like the following. Oops. Yep. It would look like this. This is negative concavity, okay? Now look at this. When the concavity is negative in this equation, this value I've circled becomes positive because in Poisson's equation, let's write Poisson's equation. Where do I write it? I'm going to get rid of this because you already understand all of this. I'm going to just write Poisson's equation. Cut. Copy. All right. So it's negative. So in other words, when the voltage has a negative concavity, it means you have a positive charge there. So what does that mean? It means positive charges produce these clumps in the ether density. And negative charges would produce dearths in the ether density. Dearth means like the opposite of a clump, basically. It means like a relative absence of the stuff. Another word for this is glut. Glut. A glut. A gult? Glut of ether density. And then let's see if I can draw a dearth. I've done my best to draw a dearth here, a place where you have relatively dearth. Okay? I've done my best to draw a place where we have high density around the, we have like, this is supposed to be like normal density out here, and then this is like lower than normal density. And so a glut is a positive charge, or I'm sorry, a glut of ether pressure is the result of a positive charge, and a dearth in ether pressure is the result of a negative charge. And so that's the physical interpretation of what Poisson, his equation, is saying. Okay, let's zoom out so you can see all of it at the same time. Yeah, there you go. There you go. And that's a good place to stop. What are your questions on this?
So far, so good. Thanks.
Okay, cool. That's really great. There's a lot here. You may consider reviewing all of this. But I think that's really good progress for now. So we'll continue. So we've now, I think we've actually, at this point, we have now completely given, well, we haven't really done much reduction here. We haven't done much reduction, like connecting it back to the observations. But what we've done is we've taken the, well, yeah, we have actually. We've taken these mathematical abstractions and we've connected them back to the experiments, like through, and we've specifically done it through the reasoning they would have had to do in order to come up with all this electromagnetic theory. Further, what we've done is we've given some hypotheses about what these electrostatic equations might mean for the nature of the ether. And hopefully that gives us a deeper understanding of what is actually going on with all of this. So thank you for joining me, audience, and we're going to keep going with this, and I hope you guys are finding this helpful for gaining a deeper insight into all of these electromagnetic phenomena. And you're going to benefit from my years and years of tutoring this and thinking constantly about what this stuff actually means. And so I can give all that knowledge to you so that you can get caught up really quickly. So you don't have to spend a bunch of time figuring it out yourself. You can use your efforts to get even further. So thank you for joining us.